So hey guys, this is something I wanted to do with my free time. So basically this channel is dedicated to explaining organic chemistry concepts and problem solving techniques. Yeah, that's it. So I'm just going to get started. So why is Orgo useful? And to answer that question, it has a lot of application in pharmaceuticals and material sciences and life sciences, especially like biochemistry or something. The thing that was really stressed in my course, which I think is the biggest benefit of both Orgo and Orgo 1 and Orgo 2, is the problem solving aspect of things. So the concepts surrounding this course make it allow critical thinking really good critical thinking questions to be written. And so this course can develop and hone your problem solving techniques, and problem solving has a lot of applications in everything, especially in medicine. And what is Orgo? So Orgo is the chemistry of compounds that contain carbon, hydrogen, oxygen, and nitrogen, and there's also like sulfur, phosphorus, and halogens, but pretty much it's the chemistry of those compounds. And why those compounds? Well, those compounds are the ones found in our body, found in living systems. So yeah, that is what organic chemistry is. And the first thing I'm gonna talk about is drawing. And so you might think that's easy, but this is what I had a little trouble getting a hang of when I was first taking the course. And it's because they already expected us to know what the shorthanded Lewis structure looks like. And so normally you're probably familiar with the regular Lewis structure, so something like, and this is just something random. Okay, so this is your normal Lewis structure, and it's good because you see what every atom is, you see the orientation, you see the bonds and everything. So that's what's good about it. What's bad about it is that it's cluttered, it's a lot for such a small compound to draw, and when you get into bigger compounds, it's gonna look like a mess. So because chemists are really lazy, they came up with this new way to draw things, and I'm just gonna draw it. So this is your shorthanded Lewis structure, and it's a lot more condensed, I guess, and that's because each carbon from your normal Lewis structure becomes a point. And so I guess I'll just draw these kind of similarities. So that carbon is that carbon. This carbon is this carbon. And this one is a little bit trickier since it's not like an actual angled point, but it's still a straight line. But yeah, this nitrile carbon thing is that one right there. So each carbon becomes a vertex or a point, and all these hydrogens that were originally bonded to our carbon just magically disappear. And they don't disappear, it's just that they're not drawn, so they're implied. And so carbon is really stable with 4 bonds, and it's very rare to see a carbon without 4 bonds. And so when you see a carbon in this shorthanded Lewis structure, you look at how many bonds it has. So it has 1 bond to this carbon right here. And then it doesn't have those three other bonds that make it incredibly stable. Well, those bonds are there, they're just not drawn. So all these bonds that aren't drawn on these carbons are implied to be with hydrogen. So this one has one visible bond, that means it has three invisible bonds to hydrogen. We can do the same thing here. So this carbon has two bonds, one to the left and one to the right, and then it also has these two other bonds to hydrogen, which don't need to be drawn again. And this one has one bond, it has three bonds, and then that one other bond is to hydrogen. We could do the same thing here, actually. So this one, you can see has one bond to the left, and then it's triple bonded with nitrogen. So all four bonds are occupied, and so that means it doesn't have any hydrogens at all. And so it's a little tricky to get all that initially, but if you just practice converting your long-handed Lewis structure and just you keep on drawing them into shorthanded, you'll get the hang of it, and you'll understand where the hydrogen atoms are even when they're not drawn, and you'll understand. Yeah, that's pretty much it. So yeah, that's drawing convention of organic chemistry. I will now do formal charge. Do I still have space? Yeah, okay. So formal charge is a measure of the electron density surrounding an atom and comparing that with the electron density it's normally associated with. And what you do with that is you compare the electron density that it has with the group number that it has. So I'll write both these, whatever. Yeah, okay, so anyways, so an electron in a lone pair is counted as one electron density unit. And a bond, I'll draw an arrow just to not confuse, and a bond surrounding an atom is also one unit. Oops, that's a V, whatever. And so you pretty much just count around the atom and compare it with the group number. So I'll do a quick example of that. And if you want, we can do the same thing. So we'll just do this real quick. So that carbon right here, we can see how many hydrogens it has. So let's see. It has two bonds with this oxygen, one more with the nitrogen, and one more with the carbon to the left. So that's all four bonds. So this carbon actually doesn't have any bonds to hydrogen. So yeah, I just did that for a quick review of that. But let's calculate the formal charge around this oxygen. So we count these units around it. So we have 1, 2, 3, 4, 5, and 6. So it has 6 electron density units surrounding it. And now we compare that with the group number. Well, and the group number is the column which the atom is in. So oxygen is in group 6, or it's in the 6th column. And because its group number is the same as the number of units surrounding it, it has a formal charge of 0. And you don't have to write formal charges of 0 since they're so common, but I did that there. So let's do this nitrogen. So 1, 2, 3, 4, 5. So 2 units from the lone pair and then 3 from the 3 bonds. So what group number is nitrogen in? Well, it's in group 5. So 5 units, it's in group 5. That also means it has a formal charge of 0. So it's the difference between those two. And so I'll do a different example. since we didn't get any formal charges from that and I drew it wrong. Alright. Okay. So, this is another molecule. We can do the same thing with our oxygen. So we have 1, 2, 3, 4, 5, 6, 7. So it has 7 units, and that means it has one more electron density unit than it's normally associated with. Remember, oxygen is in group 6. So because it has one more unit of negative charge surrounding it, it has a formal charge of -1. Now let's do the same thing with our nitrogen. So we have 1, 2, 3, and 4. So no lone pairs, only 4 bonds. It's in group 5, so it's lacking one electron density unit than it's normally associated with. And that gives it a formal charge of +1. So it's missing a negative charge, so that means it has a positive formal charge. And I think that's good. So drawing formal charge, I don't want this video to be too long, so yeah, give me feedback. I'll try to make the other videos better and maybe even like shorter. So yeah, thanks for tuning in, and I hope you found this helpful.